Hello all. We are in the last module, that means in module 4 of our course, and in module 4 we are trying to learn goodness of fit test. So this is the first lecture under this module, and in this lecture we will start by few forewords that what is the meaning of goodness of fit and why it is necessary to be implemented in statistical study, as well as we will have some idea related to the Pearson chi-square test, which is the most basic goodness of fit test, and I would rather say that this is the most initial initial device of goodness of fit test. Okay, so let's start the journey. So what is meant by goodness of fit test? An important problem in statistics relates to obtaining information about the form of the population from which a sample is drawn. In classical statistical inference, generally form of this population is hypothesized as a normal population, which is common, that mostly we assume that okay, let x1, x2, xn are coming from a normal population. Now, when we are making such assumption, we are not sure. This is a kind of hypothesis we are proposing that, well, the observations which we have collected, these are coming from normal population. So goodness of fit test is like that. You have to test whether really these observations are coming from the normal distribution, and then you can process for further analysis. But the reasonableness of such normality assumption should be checked, and that's the motive, that's the objective of studying goodness of fit test. The compatibility of a set of observed sample values with a normal or any other distribution is verified through goodness of fit test. As I have already mentioned that goodness of fit test first was initiated because of the checking of the normality, but you can make the goodness of fit test for any other distribution as well. Goodness of fit test is such a general test. That means suppose you are performing one analysis, and in the initial stage you are saying let x1, x2, xn, let observations are coming from exponential distribution. When you are assuming some distribution, some hypothesized distribution, you have to make the goodness of fit test to verify your hypothesis, and that's the ethos, I would rather say, that's the crux of the goodness of fit test. Hence, in goodness of fit test, null hypothesis is the completely specified hypothesized distribution, while alternative hypothesis is more general. So, in mathematical structure, how to write the null hypothesis? H naught is equal to fx is equal to f0. f0 is your defined distribution function of the known probability distribution, say normal distribution for all x, and the alternative hypothesis is fxx is not equal to f0x. Generally, goodness of fit test is two-sided. Usually, there are two types of goodness of fit test. The first type is designed for null hypothesis concerning a discrete distribution and compares the observed frequencies with the frequencies expected under the null hypothesis. Chi-square goodness of fit test proposed by Karl Pearson belongs to this type. And the second type of goodness of fit test is designed for null hypothesis concerning a continuous distribution and compares the observed cumulative relative frequencies with those expected under the null hypothesis. And this group is a little bigger, and it includes Kolmogorov-Smirnov test, Anderson-Darling test, Kramer-von Mises test, which I haven't mentioned here, but well, that is another modified goodness of fit test. So In this course, we will learn both of the types. So the most rudimentary one is the first type, where you have to deal with the discrete distribution, and of course followed by the second type, which is more widely used, more widely needed goodness of fit test, where we will learn this Kolmogorov-Smirnov, Anderson-Darling, etc. So let us begin today's goodness of fit test journey by chi-square goodness of fit test. In order to apply the chi-square test, the sample data must first be grouped in the categories in order to form a frequency distribution. So I know that all of you have the basic knowledge of statistical data compilation, and there you have studied the frequency distribution. So that frequency distribution we are referring here. In case of count data or qualitative data, where the hypothesized distribution would be discrete, the categories would be the relevant verbal or numerical classification. Example, in coin tossing, you will have to deal with the qualitative data. That means either head or tail, like that. So categories would be the number of heads as well as the number of tails. And one more example in this queue is a survey of brand preferences. Categories should be the brand names. Okay, so you are preferring perfume A, say, and I'm preferring perfume B, and somebody else is preferring perfume C. So A, B, C, these are the brands name of those perfumes, and your frequency distribution will be looking like that A, B, C, and how many people are going after perfume A, how many people are going after perfume B, so on and so forth. So that's the count data structure or qualitative data structure. When sample observations are quantitative, like the height of a class of students, categories would be the numerical classes chosen by the experimenter. But in such case, frequency distribution will not be unique one, and some information will be lost necessarily because of the grouping. And I hope you understand that why it is so. Because when you are dealing with height of the class, suppose someone is falling inside the class for 5 feet 4 inch to 5 feet 8 inch. So it is my discretion of grouping like that. You might not agree with me, and you can group like from 5 feet to 5 feet 5 inch. So whenever the groups are not unique, quite obviously the number of observations falling inside that group will be different from person to person, will be different from individual to individual. That's what is a problem in the quantitative data while making the frequency distribution table. So let us have 3 quick examples, and you can understand that what actually I am referring to. A quality control engineer has taken 50 samples of size 13, each from a production process. The number of defectives for these samples are recorded below. So number of defectives, 0 defective, 10 observation have no defectives at all. So 0, 10. 1 defective, 24 observations have only 1 defective, 10 observations have only 2 defectives. So it is a bright example of count data. And getting down to example 2, it's a very interesting example for the biological student, I presume, not only for biological student but for us also. In the course of a botanical experiment on the breeding of peas, a botanist obtained 556 peas, of which 315 were round and yellow and 108 were round and green, 101 were angular and yellow, and 32 were angular and green. So these are 4 categories, 4 classes, and you will have the number of observations falling in those classes. So it is a qualitative data. Now coming down to the most important as well as most widely needed problems, where you have to deal with the continuous data. Heights of 15 students in statistics major class are given below. So 140 to, you can see 140 to 187. Okay, so these are all quantitative. Moreover, that height is a continuous variable. So you have to make, continuous variable means it can take any value. So you cannot leave any value outside your classification. So therefore, category should be 140 to 149.99, 149.99 to 159.99, so on and so forth. But this is my category, clear? This is my category, but somebody else might have some other categorization. So for dealing with continuous data, you will always miss some information, lose some information. Coming down to Pearson's goodness of fit test, first we have to make up our mind that what is our hypothesized distribution function. H0 means a null hypothesis is the distribution function is equal to some known distribution function, and that is F0. Let us assume F0x is completely defined, that is all parameters are known. Let us assume n observations, qualitative or quantitative, are grouped in k mutually exclusive classes, groups and categories. We check how good the fit of F0x to those observations. That is called goodness of fit. Suppose according to the null hypothesis, the population proportion of ith class is Pi0. If the frequency in the ith class in random sample of size n is Fi, F means for frequency, the rationale of Pearson goodness of fit test statistic is to check the deviation between observed frequency and the expected frequency. Expected frequency is just n into Pi0. What is Pi0? Pi0 is the proportion for ith class. Clear? Value multiplied by the probability, that's what expectation is. So that's what is reflected by the expected frequency for each of the classes, and chi-square, this statistic is mathematically expressed by this form, that summation Fi square divided by npi0 minus n. This above test statistic is approximately a chi-square distribution with degrees of freedom k minus 1. Remember, the degrees of freedom is k minus 1 provided that npi0 is large enough for each I. Practically speaking, we always take npi0 greater than 5. That's why this is also called Pearson's chi-square test. So goodness of fit test is otherwise termed as Pearson chi-square test. Now why it is a non-parametric test? Because this expression of chi-square does not require any pre-specified distributional form to have that distribution chi-square with degrees of freedom k minus 1. No matter what is your distribution from where your observations are coming out, the Pearson chi-square test statistic will always follow a chi-square with degrees of freedom k minus 1. Clear? In general, the formula runs like, that means when you don't have the proportion idea, you are dealing with say quantitative observations, then the general formula is Fi minus Ei, observed frequency minus expected frequency whole square divided by expected frequency. Intuitively, greater the difference between observed frequencies and expected frequency, greater will be the value of chi-square. So if your observations are coming from the population which you have hypothesized, your expected frequency will be based on that population which you have claimed in your null hypothesis. So if your observed frequency is very close to the expected frequency which is coming from the population idea, then what you can conclude you can conclude that the observations at your hand are the part of or the sample from the hypothesized population which you are claiming, right? So right from that intuition, if you can see your observations or the frequency of your observations are very small, while the expected frequency which you are finding out from the population hypothesized, there is a long gap, there is a wide gap, then what will be your conclusion? That those observations are not coming from the population you have claimed. So that is give you the rejection rule for the chi-square test. Hence, a higher value of chi-square will indicate rejection of null hypothesis and the falsity of the distribution function of F0. We reject the null hypothesis at alpha level of significance if chi-square calculated greater than chi-square alpha k minus 1. So, chi-square alpha k minus 1 is your tabular value, right? And accept otherwise, since here we see how well expected frequencies are in agreement with observed frequency, hence this test is called a goodness of fit test. Now you can understand the meaning of the terminology, goodness of fit, how good your fit is to your data. In order to claim a fit as good, it is necessary to achieve the acceptance of the null hypothesis at higher level of significance, say a level like 0.3 rather than the usual alpha is equal to 0.01 or 0.05. In terms of p-value, higher the p-value, better would be your goodness, that term goodness. Remember, in practical situation, some parameters of the population, suppose you are estimating normal population, so some parameters of that normal population, so normal has two parameters, one is mu, the mean, and another is the variance, sigma square. Suppose you don't know that mu and variance, then you have to make the estimate of those parameters. And for this estimation method, generally method of moment is considered. What is method of moment? That sample mean is a better approximation of population mean. Sample median, sample variance is a better approximation or better estimate of population variance. Then if pi0 hat means the estimate, be the estimator of population proportion, then the goodness of fit test statistic will be chi-square. You see that Fi minus NPI0 hat means you are replacing that NPI0 figure by hat whole square divided by NPI0, and after calculation it will turn to a very lucid expression, summation Fi square divided by NPI0 hat minus n. But you have to remember, when you are estimating those unknown parameters, then subsequently the degrees of freedom of chi-square will be receding. So earlier it was chi-square with degrees of freedom k minus 1, but after estimating say r parameters, then degrees of freedom will be k minus 1 minus r. Okay. Let us have a manual problem solving. In this course of a botanical experiment, already I told you 556 peas, of which 315 were round and yellow, 108 were round and green, 101 were angular and yellow, 32 were angular and green. So 4 categories, clear? And according to the genetic theory, such peas should be obtained in the ratio of 9:3:3:1. Remember that Mendelian theory right from your biology class? So that's what is reflected here. So 9:3:3:1, that is your population proportion. So what is your null hypothesis here? Null hypothesis is P1 is equal to 9/16. 9:3:3:1, altogether 16. So the proportion turns to be 9/16, P2 3/16, P3 3/16, and P4 1/16. Now we will make that frequency distribution table. Here you can see class 1, 2, 3, 4, 4 classes. Observed frequencies are given as 315, 108, 101, and 32. And expected frequency, already you know the formula. It is NP1, NP2, NP3, and NP4. Clear? So P1 you know 9/16. So just the multiplication. N is your total number of observation, and that is 556. So 556 into 9/16. What it turns out? 312.75. Similarly for NP2, NP3, and NP4. Remember, your total of expected frequency should be 556. This is just a conventional point of having the total frequency as it is in the context of observed frequency. So the total frequency under the observed frequency category will be matching with the total frequency with the expected frequency. So you will have to make some minor adjustment to get this round figure 556, but that is not very significant. Now coming down to the calculation of the Pearson chi-square, observed square divided by expected, and that is the calculations, and it is means summation Fi square divided by NPI 0, and that sum turns to be 556.470. Just grab one calculator and you can figure out what is the chi-square chi-square calculated value, that is 0.470. Now look at the chi-square table and make a comparison. What will be the degrees of freedom? Once you have 4 categories, the degrees of freedom will be 1 less. So 4 minus 1, 3. So chi-square tabular value, this is the chi-square table, and you are aware how to look at the chi-square table. Here you will see that 3 degrees of freedom is 3, and we are looking for alpha is equal to 5%. So 0.050. Alpha is always from the right hand side. So look at this dark portion. This is 0.05, and what you can see, the tabular value is 7.815. So this is your tabular value. As your calculated value is less than your tabular value, you accept the null hypothesis. And what is the final conclusion? The experimental result is compatible with genetic theory, and this problem we can solve using R, and we'll check on the decision by the p value. Okay. Let us have one more quick example, and this example is a count data example. A quality control engineer has taken 50 samples of size 13, each from a production process, and number of defectives are recorded below. So already we have seen this data during the discussion of our examples. So these are your observed frequency, and one additional information is given here. And what is that additional information? Not to be missed, that the distribution of number of defectives follow a Poisson distribution. So that is your follow a Poisson distribution, means that is your hypothesized distribution. Your null hypothesis will be observations are coming from Poisson distribution. Now as you know, Poisson has the parameter, a single parameter. So what is that parameter? That is lambda, but lambda is not given here. You have to estimate the lambda. Clear? So how to estimate? Lambda is the population mean for Poisson distribution. Therefore, population mean can be estimated through the sample mean, and we can figure out lambda hat, which is the sample mean of this frequency distribution table. So what is the sample mean? You know the technique. 0 times 10. 0 is your x size, and F-wise it is a frequency table. So 0 into 10 plus 1 into 24 dot 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 plus 5 into 1. Okay. So you have to make all of the multiplication like. That's why I am saying the dot dot dot. Okay. So lambda will be turning out to be 1.3, and by this lambda we are able to figure out the expected frequency. So what will be the expected frequency? That total number of observation, which is 50, into probability of x is equal to 0, probability of x is equal to 1, probability of x is equal to 5, so on and so forth. Clear? So I mean, just for one example, for x is equal to 0, expected frequency is 50 into probability x is equal to 0. You know the probability mass function of Poisson distribution, and just replace the estimated lambda over there, e to the power minus 1.3, 1.30 divided by 0 factorial, and it turns to be 13.625, because after multiplication it will be 13. Similarly, for x is equal to 1, expected frequency turns to be 17.715, and for x is equal to 4, expected frequency is 1.620. So you have to calculate out all of these things. In fact, in case you don't know the probability mass function conversion of a Poisson distribution, nothing wrong in it. Don't get anxious, because we have R in our hand, and in R you can use the command dpoise. Dpoise, look at this, 0 means x is equal to 0, and 1 means 1.3 is the value of estimated lambda. So that will give you probability of x is equal to 0. What is probability of x is equal to 0? That is 0.2725. Now multiply 2.2725 by 50 and you will have the same answer. So therefore, don't get anxious, don't get worried that once you don't know the Poisson conversion. Clear? So finally, the tables for which we can jot down the expected frequency and the observed frequency is like that. Now getting down to chi-square, see one more point. Here there are how many classes? 1, 2, 3, 4, 5, 6, 7. But 6 or more, this class doesn't have any frequency. So we can omit it, we can strike through it. Number 1. Number 2, as I told you, total expected frequency must be 50. That will match with the total number of observed frequency. So you have to estimate the last class expected frequency. How? By 50 minus the expected frequency of this class, this class, this class, this class, and this class. So that's what is written here. Here 6 classes have non-zero frequency. Clear? So what will be the degrees of freedom? Be very cautious, because that will guide you towards the determination of degrees of freedom. So k minus 1, 6 minus 1, 5. But there is 2 more points. What are those 2 more points? 1, we estimated lambda, so we have to lose 1 more degrees of freedom. Clear? So initially it was 5 minus 1, so 4. And another point, we merge last category x is equal to 5 by the adjustment. We have adjusted. How did we adjust? I told you, just to make this total frequency 50, because you understand the 6 or more, it has some very, very low probability. We are not considering that low probability. We are just ignoring them. So because of that ignoring things, you have to make that adjustment. Thereby, we are losing 1 more degrees of freedom, and that will get your final degrees of freedom of the chi-square distribution as 5 minus 1 minus 1, that is equal to 3. Okay. So basically we'll have to go to the chi-square table and look at the tabular value for chi-square with 3 degrees of freedom. Now the rest is extremely easy. Chi-square calculated value, you know the technique, and it will come as 4.231. I am not going into the details. You can grab one calculator and you can solve it out. Tabular chi-square 3 value at 5% level of significance is 7.815. Since chi-square calculated less than chi-square tabular, H0 is accepted. Therefore, number of defectives follows a Poisson distribution. Now, coming down to the R code for these couple of examples, R will make our life easier, you know. So that's what we are going to experience now. The first example, I have made the screenshot here. So the first example is pretty easy example. The observed frequencies are given are 315, 108, 100, 132. That means the example of that botanical experiment. And the population proportion is, let me call it by that probe, and it is 9 by 16, 3 by 16, 3 by 16, 1 by 16. Only thing which you need to remember is the syntax. Chi-sq means square dot test, data is given, and P means the probability, population proportion. P means population proportion. So 2 arguments needed, and in our case P is equal to probability, and if you run this program, you will have the chi-square value as 0.47002. Look at the P value, which is quite big. The same problem we handled by looking at the table, the critical value comparison, and here we will have the same conclusion looking at the P value. P value is extremely high as compared with 0.05, so we failed to reject the null hypothesis. For example 2, let me open my R window because I would like to show you how the R is running, and thereafter we will be coming down to my PPT. Okay, so example 2 we are talking on. These are the number of defectives. I have named that number of defectives by DEF. How many defectives are there? 0, 1, 2, 3, 4, 5. Intentionally I have omitted that 6 or more class because that class doesn't contain any non-zero items. So there are 6 classes. Number of sample under each class, C is 10, 24, 10, 4, 1, 1. So these are the observed frequency. Now this part you will have to learn how to merge number of defectives along with the observed frequency. This merging can be done by cbind. Okay, so let me run this. Cbind. So this is our data 2. Now we are trying to find out the chi-square. Term-wise multiplication, summation fi xi, that is what we are intended to do. So this is now estimating lambda. Lambda is nothing but the mean, sample mean. So lambda is equal to sum and the term-wise multiplication, defectives times number of samples divided by sum of number of samples. Number of sample is 50. So I would recommend you, after running each of the line, just try to have a look over the result you are obtaining. Clear? So what is lambda? Okay, let us see whether this lambda matches with our manual calculation. Yeah, it matches. It is 1.3. And the next one is a little, would say a little tricky. that initialization of population probability vector. We have to figure out probability x is equal to 0, probability x is equal to 1 when x follows Poisson with the estimated lambda as 1.3. So that in that case we have to use a continuation loop, and that loop is done by for loop for I in 1 to 6. We have 6 classes, so for 1 to 6. Okay. So this is called initialization probability C000. So this is called initialization. Now we will improve that initialized vector by our calculation through the for loop. Clear? Now let us have a look what the probability is. Fine. Probability for x is equal to 0, that is 0.2725. In fact, you may make a match with the manual calculation we did in our PPT presentation. Probability of x is equal to 1, that is 0.3542, so on and so forth. Then what will be the chi-square? Test statistic, number of sample, p is the proportion, here it is probability. And one more thing not to be missed, that in chi-square test syntax you have to incorporate rescale.p is equal to true. That means that you are instructing R to make the total probability 1. Everything I have written as a comment just above the syntax line. So do not miss those comment lines. That hash line means the comments line. Okay. So let us run this line. Okay. So since you are doing rescale.p is equal to true, that's why this warning message pop up that it might be some approximation. Clear? So what is the chi-square value? That is 4.612, which is very close to ours. Probably we get 4.14. I'm not, just have a look over there. And what is the expected frequency? You can do that as well. T1, I have named the expected frequencies as T1, and T1 is 13.65. We have manually calculated, make a check. 17 point for the second class, it is 17.7541, so on and so forth. So let us get back again to the PPT. Okay, so that is the screenshot. Now look at the value of the chi-square 4.612, that exactly matches with our manual calculation, but look at the degrees of freedom, it is 5. So it is wrong. Why it is wrong? Because R will see how many classes you are giving R. You are giving 6 classes, and mechanically R will give you the degrees of freedom 6 minus 1, that is 5. But it is you who has to fix with all your logic. Already I told you the logic, that what would be the correct degrees of freedom, and thereafter you can go for the p-value. So the p-value which is showing here, it is based on the chi-square degrees of freedom 5. This is based on chi-square degrees of freedom 5, but it is wrong. Remember, it is wrong. So we'll have to go for chi-square 3, p-value for chi-square 3 degrees of freedom. So I will ask you to be very cautious of doing the problems using R. These two problems, these 2 points, already I have mentioned, manual calculation and value obtained by R are little different. And look at the degrees of freedom. The degrees of freedom fiasco has to be handled by yourself. Okay. So chi-square value is correct, but p-value is not correct. So either you can go to chi-square table for making the decision, or you can use p-chi syntax in R. You see, I have drawn here. So P chi-square x degrees of freedom should be 3 here, which will give you chi-square less than equal to small x. This is the thing, and P value will be always towards the right side. So 1 minus, so whatever P chi-square is giving, P chi-square is giving this part, okay, this part, and you have to go for that tail part. So 1 minus P chi-square, and this is your obtained chi-square value, 4.612 or 4.4, whatever you have obtained in manual exercise or by R, 4.612, and degrees of freedom is 3, and look at the P value is 0.20 greater than 0.05. We failed to reject the null hypothesis. So that's what you need to be very cautious while dealing with the degrees of freedom. Clear? So what to do if there are small expected frequency? That means NPI 0 is less than 5. If the assumption of chi-square test have not been met, any category has expected frequency less than 5. There are two way out. One is Fisher's exact test can be implemented, and in Fisher's exact test we have to calculate the exact probability, not by approximation. And another possible way to merge categories together, of course, this type of merging will cause loss of information. So that's the Pearson chi-square goodness of fit test, which is most widely used goodness of fit test, but it has some lacuna, as we have seen, because of the classification, because of the approximation. Sometimes it has the tendency to lose the information. So we have to deal with it with some finer, with some advanced goodness of fit test. Next class we will learn this. Thank you. So these are the P values. As you can see, P value for testing the equality of median between drug A and drug B turns to be 0.045. P value for testing the median between drug A and drug C, that is 5.6 into 10 to the power minus 6, and P value between the median of equality of the medians, I mean to say, drug A and drug C, that turns to be 0.045. Now, what will be your take on if you are fixing your alpha as 0.05, then for this comparative calculation, for this post hoc test, you have to make the checking of the P values with respect to the alpha by 2. Okay, so that will be 0.025. So if you can see 0.045 is bigger than 0.025. Most of the time people make a mistake here. They stick to the original level of significance, but while doing the pairwise comparison, you have to divide the alpha by 2. So 0.025, and with respect to this 0.025, just test the validity of this P value. 0.045 is bigger than 0.025. Therefore, the median between drug A and the median of drug B, they are the same. But look at 5.6 10 to the power minus 6, which is extremely low. The P value is pretty low with respect to 0.025. So, the median of drug A and the median of drug C, they are not different. Sorry, they are different to each other. ঠিক আছে, হয়ে গিয়েছে।